by doing land reclamation first. Well, you also know we don't have sand or good fuel materials for land reclamation. So sometimes we may have to use very soft marine clay and dredge it from seabed as the fuel materials for land reclamation. What Malaysia, Singapore, as well as many countries in Southeast Asia are also suffering from sea level rise. Well, by prediction, maybe half, or I should say 1/3 of Singapore will be inundated by 2000. In fact, land reclamation is also one of the measures to tackle rising sea level. So in fact, this is what has been proposed for Jakarta. So some of you may heard the proposal to construct a giant seawall as shown in the picture below. So over here, not just having a wall, and there's also some land reclamations involved. And the wall can help to form a coastal reservoir, as you can see in the graph. So the coastal reservoir will also provide the clean water to the Jakarta city. So this was a proposal quite some time ago, but however, it has not been implemented or has not gone into practice. So if we are going to use the seawall to form a coastal reservoir, and then we will also have to dredge the 13 rivers within Jakarta. Okay, just make sure the water collected will be clean enough. So we will need to do dredging of the seabed. So as a result of the dredging, so the dredged material can be used as a land reclamation, for the plan which we have just seen. So in other words, for the Jakarta project, if we are going to, or if Jakarta is going to go ahead with the project, then there will be some land reclamation to be carried out. So land reclamation using very soft fuel materials would be one of the options for them to consider. But the first question some of you may ask is it feasible to use dredged slurry for land reclamation? And the answer is yes. I mean, there are a number of examples. So for example, the port of Brisbane, and so part of the land reclamation is by using the river mud and dredged for a maintenance dredging from the seabed. So those dredged mud are used for land reclamation for the Brisbane port. And also in Tianjin or Wenzhou, so which are two coastal cities along the east coast of China. Well, of course, Tianjin is further north, close to Beijing, and Wenzhou is somewhere near Zhejiang province. So both cities have been using marine clay and dredged from the seabed in a slurry form for land reclamation. And the reason for that is because for both cities within the vicinity of 100 kilometers, so there isn't any sand fields for them to use for land reclamation. So in fact, in Tianjin, and they have already reclaimed more than 190 square kilometers of land and purely using dredged slurry. And this is actually more than the land reclamation made altogether in the past years for Singapore. For dredged clay, and we have two types. One is using a grab dredger and to collect a lumpy soil. Okay, as you can see from the picture on the left. So in this case, the water is the soil is not mixed with water. In other words, the water content of the clay is not very much increased. So this will be a better scenario. But on the other hand, I'm using a grab and will be relatively slow. So in fact, for the land reclamation in Tianjin or Wenzhou, and they are using the second form, and that is using a suction dredger to dredge so-called clay slurry and to pump into where land reclamation is going to be carried out. Okay, so this is in the Chinese is called the tree tian. So tree tian refer to a hydraulic fill. But this hydraulic fill is not by using sand, but by using mud. What the difficulty in the use of soft soil, particularly slurry for land reclamation, is the top is too soft, and for workers, for the machines to go on top to carry out soil improvement work. Even if, for example, you want to install PVDs, you must have a working platform, for the PVD installation rigs and for all your machineries to go on top. It is not possible, even for a concrete block to stand on top, or not for the workers, to stand on top of a very soft soupy mud. So the key technical challenge is how to form a work platform. In my opinion, there are methods. There are a number of methods, but the method to be used is the one with the lowest unit cost. And the reason is very simple. For land reclamation, we are talking about millions of cubic meters of fuel. So if you can save $1 per cubic meter, so you are saving millions of dollars. Now let's discuss what are the methods available for the formation of a working platform on ultra soft ground. If we are going to put a weak, let's say, concrete block on the soft ground, it is not going to be stable. It's going to sink into the clay, as shown by this graph. But however, if we put a layer of sand, so for example, put in this particular case, it's about 0.8 meters of sand. You probably will have the sufficient bearing capacity for concrete block, which is about 1 ton or 20 kilonewton per square meter to stand on top. So as can be demonstrated by this video. But however, to put a layer of sand on top of very soft clay is also challenging. But before I talk about that part, okay, let me just give you a very quick review of what are other methods available. Okay, I mean the second method is for using cement. So one is by using a mixing machine as showing over here, and just to mix the top a few meters of soil and using cement. So the machine is showing over here. So basically you have a cutter. So the cement is injected at the position where the soil is cut by the cutter at the same time, and the cutter is rotating and mix the clay and together with the cement. So one application is for a pot in Spain, as you can see from the picture on the left. So a top layer of, if my memory is correct, is about 1.5 meters of a working platform is formed using this method. And the picture in the middle and on the right is for another example. So this is on the highway construction at the bottom of a Tai Lake. Tai Lake is somewhere in Anhui and Jiangsu of China. So Tai Lake is a big lake. So a highway is going to be constructed at the bottom of the lake, and it is an open cut construction. So in other words, you will have to form cofferdams. You can see from the background. Okay, so you can see a row of walls. So this is actually the cofferdam to make the lake where the road is going to be constructed as the middle of the coffer dam, and then you have to mix cement with the mud of the lake bed, to form the base for the highway. So the same method was also adopted for this particular project. If the soil is very soft, if the soil even have water on top, so you may need to use a machine like this, so like a floating mixing barge for the mixing tools to be floated on water, and before you can use the mixers at the toe and to do the mixing. So you can control the cement in such a way, the working platform will not have a very strong, very high end shear strength. And in the case for Spain, and the end shear strength was controlled to be somewhere around 75 kPa. Oh, now let's go back to how to place a layer of sand on mud on very soft ground. Some of you know Professor Brown, so he was my former boss. He taught at NGO for quite a number of years before his retirement. He proposed a method as early as 1987. So what he said is, okay, if we have very soft ground, and in fact at that time he was thinking more for the construction on top of some of the minings in Malaysia, because you have some Qing mining, so now you have some ponds formed as a result. So if we are going to, for example, to build a road on top of it, what Professor Brahms proposed is to put a layer of gel fabric, and so use these rings, as you can see, is to form a sort of a berm to anchor the layer of gel fabric. Then on top of it, you can use a bulldozer and to push some fingers, as is showing over here. So you push your fingers on top of the gel fabric, under the weight of the fuse along the fingers. So you create some tension in the gel fabric. So eventually you will probably will be able to use the gel fabric to sustain the fingers. Then after that, you can spread the fingers, that way, and then to form a layer of fuel, a layer of sand fuel on top of the gel fabric. And Professor Brahms has also, did some analytical work and to develop some solutions for the calculation of the tensile stress in the fabric, as well as the amount of settlement involved for the berm to be stable. And he has also developed the design charts, as showing over here, for the bearing capacities of each fabric to be calculated as a function of number one is the width of the finger, and for the graph on the left is for 2 meters, and for the graph on the right is for a width of the finger of 4 meters. And his variables are the distance between the fingers, which is L2, which is ranging from 4 meters to 10 meters in his chart. He has also given solutions for the fabric with different tensile strengths. So for example, whether it's 160 kilonewton per meter or 40 kilometer per meter, and the amount of settlement as well as the bearing capacity involved are different. So this is what within our expectation. We actually wanted to use Professor Brahms' method for one of the projects in Singapore, which is using mud, using pumped marine clay into a pond. But however, we encounter difficulties because even if you put a layer of fabric, but the ground is still so soft, and it is very difficult for a finger to be formed. And even though the finger can be relatively narrow, and the height of the finger can be small, because sometimes you know, it's just like a waterbed. There's a sand will not form a strip. Sometimes it lump sum into a chunk, and so that will sink down and to defeat the purpose of having a finger. So to overcome this difficulty, so we thought it's probably easier to form a finger and to use a gel textile tube. So if we put a gel textile tube, we can just pump the sand into the tube, and in this way, you know, the fingers or the berms can be formed. So we did that. So it was better than just putting sand on top of the fabric to form a berm. Well, because now it is a cylindrical, or you can see it's oval type of fingers, rather than, you know, like a berm, as what proposed by Professor Brahms. So the analytical solution may also need to be different. So my PhD student, Dr. Chen Hao, has developed another set of analytical equations for us to calculate the tensile strength in the gel fabric, as well as the bearing capacity of the gel fabric, as well as the settlement, I mean, for a given weight for the fingers, etc., etc. So he has developed, you know, not just design charts, but also, I mean, spreadsheets solutions, you know, for easy applications. So nowadays, because of the convenience of computers, you really don't need to have you know, charts anymore. You can just you know, put numbers into your Excel spreadsheets, then all the graph will be generated automatically. So if by the way, this is published in gel textile and the gel membrane at 2021. So if any of you is interested, I mean, I will be more than happy to share this paper with you. So the so-called modified Brahms method was attempted for one real projects. So the picture showing here are some of the construction processes. So firstly is the placement of a layer of gel fabric. As you can see from here, the gel textile was used. So because the gel textile was actually relatively heavy, it is not that easy to pull, you know, from one set of the pond to the other set. You can see the forms was also used, you know, to enable the gel fabric or gel textile to float on top of the water. A cringe is used, you know, to pull from another set. Even though it is not that straightforward, because sometimes you know, the joints of the gel fabric can tear. So if that's the case, you know, you have to, you know, improve the seams to make sure and the seams will not open. Then even after the gel textile was placed, and after the so-called the gel tube was used to form the berms, to form the fingers, and subsequently for this particular project, we actually observed a burst. So burst of the gel fabric. So in other words, the mud is now shooting out from the opening. So the mud actually covers quite a larger area of the constructed set. Okay, so once you have this, so this is considered as a failure in terms of the construction processes. So in other words, even if we have used a gel tube, and sometimes if your mud is very soft, if your mud has a very high water content, so it is also difficult to apply this method. Well, this is for one project. Then for another project in Singapore, excuse me, I cannot mention the name of the projects because I've signed a lot of confidentiality agreement, but nevertheless, I can show some pictures. So we thought that while we have learned our lessons, so one layer of gel fabric, gel textile, may not be strong enough. So this time we put the gel grid below, and we put geotech star on top. So we thought, with this, the strength of the gel grid plus the geotech star will be strong enough to against any any bursting or any rupture. But as a matter of fact, in this particular project, a bursting took place again. So the mud actually showed out and covered quite a larger area of the gel grid plus geotech star. But it not just cover, some of the mud will just sink down, and this causes a lot of inconvenience, a lot of time for the remedy work for the cleaning up. Well, the next solution, of course, is by using bamboo. Okay, you may say, well, even if your gel grid is not rigid enough, so the bamboo will offer not just the elasticity, but also give you the rigidity, and so for you to have a better chance for the sand layer to be placed on top. Indeed, yeah, in China, this bamboo mattress has been adopted. In fact, for one of the projects in Malaysia, as shared by Mr. To, I took from his paper and his co-workers' paper published in 1994 in geotech science and geomembrane. And those are the figures taken from his paper, and he was using Polyfab TS 700 at that time. Even with this bamboo fastening, as reported in this paper, and the bursting took place again. So in other words, even with bamboo fastening, there's no guarantee, the bursting will not take place. Well, to conclude, you can use the Brahms method, you can use a modified Brahms method, you can use a bamboo mattress for the formation of a working platform by put a layer of sand, a layer of good earth on top of slurry, and with the help of either geotech star or gel grid plus geotech star. But however, there is no guarantee, bursting failure will not take place. So basically, it may not take place. So you need to run the risk. So, but is there another way to enhance our reliability slightly better? So it's for that reason. So we proposed one method, which is the so-called short PVD method. So basically, what we say is, okay, since we need to form a working platform, can we use PVDs which are installed only a few meters into the mud? We improve the top layer first. So the whole purpose of improving the top few meters of mud is for the soil to gain a little bit of enduring shear strength. So if you do final element analysis, you will see it makes a big difference whether your enduring shear strength is 1 or 2 or your enduring shear strength is 5 to 10. If it's 5 to 10, your stability is much enhanced as compared to the soil without any enduring shear strength or with only a 1 or 2 kPa of enduring shear strength. So once you have a working platform, and now you can do normal soil improvement work. You can let your vertical drain installation rig, you can get your lightweight trucks to go on top and to do further soil improvement. So the construction procedure by following this proposed method and can be illustrated in the following cartoon. So if we can still use a lime pea soil, and if it's not super larger scale project, we can still grab soil and use a barge to transport the lime pea soil into the land reclamation site. Then we dump it using bottom open barge. But however, this can only be done to a certain water depth, let's say to maybe -3 MCD, if 0 MCD being the mean sea level. Then after this, it will be difficult for you, to dump lumpy soil anymore. So you have two choices. One, you can top it up using sand, or if you don't have sand, you can still top it up using dredged clay. But this time you have to use, hydraulic fuel. You have to use, pumped slurry. Because pumped slurry is going to have a lot of compressibility, a lot of settlement, so you will need to maybe extend your deck temporarily for you to put in more fuel materials. Then after consolidation, you will go back, to the elevation which is required. So if you are going to do this, then it will be difficult for you, to go on top to do any soil improvement. But yet you can still, use a special machine, which I'm going to show you in after this slide, and to install just a few meters of PVD, and you can do it manually. Afterwards, I can show you, or you can just use a very light machine, and for this purpose, for the installation of few meters of PVD into the mud. Then after that, you can, go on top to put a layer of membrane. Once you have the membrane, you can use a vacuum pump to start to consolidate these 4 to 5 meters of mud. So for the 4 or 5 meters of mud reduces the water content to gain a little bit of enduring shear strength. So after that, you can put a layer of sand fill, and this time you will be able to put let's see, maybe one. In fact, 1 meters of sand fill is sufficient. 1 meters of sand fill on top, not just to give you the trafficability, also enhance the bearing capacity, and then for now your vertical drain installation rig to go on top to install PVDs all the way, not just through the clay fill materials, but also to the bottom of a soft seabed. And then after that, you can continue to use a vacuum to do further soil improvement. The vacuum has a limitation of 80 kPa as its maximum surcharge. But however, if you need to use a higher surcharge, what you have to do is, after vacuum consolidation, or maybe in the middle of vacuum consolidation, so once your clay has gained enough enduring shear strength, and you can go on top to put a fuel surcharge to top up your surcharge if you need a surcharge which is more than 80 kPa. Yeah. So showing over here are the different ways for us to install PVD into mud. You see some are actually on top of water. So the picture on the left is by just using a rod. A rod put, you can put a piece of metal, so for the PVDs to be inserted here, and because it is mud, it doesn't have much of enduring shear strength, so you can just ask a worker to push in this rod into the ground and to install PVD, or you can have a floating barge as shown in this picture, for you to install a few meters of PVD, or you can just you use a floating platform showing in this picture to install PVD. I'm not sure this is a video. This is not a video. Okay, yeah. Later on, I'm going to show you a video. So once the PVD has been installed, you don't need to put a sand blanket. For those of you who are familiar with vacuum preloading, so the first step is you install your PVD. The second step, you install your horizontal drainage pipe, and the horizontal drainage pipe need to be embedded in a layer of sand, so we call the sand blanket. But there are ways for you to do away with the sand blanket. So that is by connecting your PVDs directly to the horizontal drainage pipe. So I'm going to show you the pictures after this. So once your PVDs are connected and to the vacuum pump, you can start to switch on your vacuum pump, and you can start to do your vacuum consolidation as shown in this cartoon. Well, in fact, this method has been adopted for land reclamation in Singapore. In fact, this case study has been published in a conference in Singapore a few years ago. This is just before COVID, 2017. That's a typo, 2017. So you can see the fuel materials is mud and dredged from the seabed. You can see the after fuel has been placed, there's water on top. The moisture content in the slurry form can be as high as 120 to 130 kPa. Unit weight at this stage, of course, is very, very low. And this is a marine clay. So in other words, the liquid limit is very high. And the void ratio is also very high, as you can see from here, okay, as high as 2.6. The first procedure is for this particular case, a layer of gel fabric was placed. So this layer of gel fabric is just for safety. Okay, so probably make it easier for the workers to work on top. And if it's very soft, what you have to do is you have to use the foam. You have to use the foam for the workers to go on top. Although this foam is not shown in this video, because this video was taken at a relatively firm ground. So I'm going to show you a video to see how the PVD is installed just by a worker. You can see how soft when the worker, exert the force, the water is coming out. Yeah, so this is how the PVD is installed by manual labor. Of course, you can say, wow, this is very labor intensive. Yeah, don't worry. I have another example to show you on how the PVDs can be installed using a very light machine. Once the PVD is installed, the PVD will be connected to the vacuum distributing pipe, as shown in this picture by a special coupling. Okay, so this coupling is actually easy to connect. And for the second case study, I'm going to show you some more pictures on how this is going to be connected. So once your PVD is connected to the drainage pipe or vacuum distributing pipe, as shown in this picture, and then you can put a layer of membrane. Sometimes you may need a layer of membrane and need another layer of protection, or even need more than 2 layers of membrane. But nevertheless, once you have put the membranes, and you can start to use your pump to do vacuum preloading. So for this particular project, at one monitoring point, the settlement up to 800 millimeter was incurred within, this is 55 days. In terms of moisture content, the water content has been reduced from the initial 130 and to the current 60 to 70%. At one position is the reduction slightly more, is from 60 to 70%. So at this moisture content, and if you use a few vein shear, so your soil now will gain enriched strength from originally 0 to now 10 to 20 kPa, as you can see from the vein shear strength showing on the red. So with enriched strength of somewhere between 10 to 15, with 1 meters of sand fill, and I think you will have enough bearing capacity, for the ordinary vertical drain installation rig, not a very heavy one, ordinary one, to go on top to start to install PVDs. Yeah. Just now is one case in Singapore, and recently I was involved in another land reclamation work in Indonesia. The same method was adopted. And just to show you how soft is the ground, so one worker has insert a bamboo pole into the ground easily. This is not a video. This is just a picture to show you the action when the pole was pushed into the ground. And the picture on the right is showing PVD installation rig. And in this case, the rig is 5 meters tall because only 5 meters of PVD is required for the formation of a working platform. The ground is still relatively soft. In this case, a layer of bamboo mattress was placed before a layer of gel fabric was put on top, so the workers now can work on top of the bamboo frame and to go to do some installation of PVD, as well as connecting your PVD to your horizontal pipes that can do some light construction work. But for at that time when we visited the site, and we still have to use timbers for people to work on top, because even with a bamboo mattress, the ground is still very soft. Yeah. So the picture showing here is how the PVDs are installed with the horizontal drainage pipe, as you can see from here. And this is actually a video. Let me see whether I can play the video. And the PVDs were installed using the lightweight PVD installation rig, as you can see from the early picture showing over here. Yeah, so this is how the PVDs are connected. And so here is the picture showing when the membrane has been placed, when the vacuum has already been applied for some of the sections. You can see from the picture, this is a big project. It's not a small area for land reclamation. Yeah. So in other words, I'm using the short PVD followed by normal soil improvement. At least this method is feasible. At least it has been used for 2 projects, one in Singapore, another one in Malaysia. But even though, in my opinion, even this method has its own shortcomings, that's because there are still a number of difficulties involved in this method. For simple reason, because PVD is used. So what are the difficulties? Number one, and we still need a working platform, which is difficult and time-consuming to build. Although we can see we can use short PVD, but for the consolidation on the short PVD, you will still take at least 2 to 3 months. So this is time-consuming, and also it is not that straightforward for you to install the short PVDs and for you to do vacuum consolidation. And the second problem is the soil improvement can only be carried out after all the fill materials has been placed, and that may take a long time. Okay, if the fill materials has not been placed, so this will add on to the time, to the construction duration, in addition to the 2 rounds of vacuum consolidation. And number 3, it is difficult to design. You can imagine, we actually do not know how much the soil is going to compress. Of course, we can calculate, but however, the calculation is extremely difficult, simply because we are dealing with a high water content soil. And for this soil, you even cannot do an odometer test. So how are you going to determine CC, pre-consolidation stress, for you to calculate the settlement? And furthermore, when the soil has a high water content, and in fact, they are not in the soil yet. So in other words, the clay particles are not in contact with each other yet. So they are sediments, they are not the soil yet. So it's difficult to calculate the amount of settlement. But But by saying that, we have a rough method for you to estimate the settlement for clay slurry. And the paper will be presented in the coming Southeast Asian Geotechnical Conference in Bangkok. So for any of you, you are going to Bangkok, so we may have opportunity to discuss the topic on how to calculate the settlement of clay slurry. But nevertheless, it is difficult to calculate. Particularly, it is difficult to have a precise prediction. Number three, vacuum can only be applied section by section. So if you are going to have a larger scale of land reclamation, so you will have to do it. Sometimes you may have to do a small partitions in between for the membranes to be anchored, for one section, and before you can do soil improvement for the other sections. Other limitations is the vacuum pressure is only limited to 80 kPa. And it is for this reason, okay, and if you are going to do land reclamation, not just for soil improvement, for the Singapore case, which is land reclamation. So in other words, they can use a different method. For the Jakarta case, the fuel material has been dumped quite a number of years ago, and the fuel materials was mud, either from maintenance dredging or from dredging for other purposes. So they dump all the clay over there. So that clay has already been there. But if you are doing land reclamation, so the clay fuel materials has not been placed, and then you actually have a better method, rather than to wait until all the fuel materials has been fully placed, and before you go on top, to do shell PVD to form a working flat platform and to do further soil improvement work. And that method is the so-called use of horizontal drains for land reclamation. And by the way, the use of horizontal drains is not new. So some of you may have heard when Professor Li Xinlip was with us. So he actually have proposed using sand layers to form horizontal drains. In fact, pilot test has been carried out in Singapore and very near the Changi Airport, as you can see from this picture. But however, at that time, if you are going to use sand layers, okay, and it is very challenging to do quality control, because for those of you will know it's very difficult to place let's say 0.5 meter to 1 meter of sand layers, on the water into soft clay. So for that reason, I mean, we have proposed something else. But before I present something else, I also have to say, horizontal drains has been attempted for this purpose. So in the past, people has been using vertical drains to put them in a horizontal way to act as horizontal drains. But however, this method may not be working all the time for a number of reasons. Reason number one is if each PVD is placed individually, in other words, the PVDs are not connected, the PVD can be everywhere. So it's very difficult for you to ensure the PVD will form a grid which is used for you to do design. So in other words, you have to do design by assuming a certain spacing for the horizontal drain, a certain vertical spacing, this and that. And that spacing may not be maintained once the construction is carried out. So in other words, it will be difficult for you to do design. And the second one is if you just put the individual drains, actually the drainage is rather limited. Okay, so we didn't realize this until we have done further research and using our method. So what is our method? Our method is to put drains which can still be PVD or can be other specially designed drains, and to be placed on top of a layer of geotextile sheet. So as shown over here. So in other words, you will come as a piece of blanket with drainage enhanced at where the drains are installed. So for that reason, our product is called the horizontal drainage enhanced geotech style sheet. So it is not just called the horizontal drain. Of course, you can adjust the spacing to cater for your design need. We actually have done some larger scale laboratory model tests. I have to say, so far, this method has not been really used for any larger scale real projects. So if any of you are interested, well, we can always discuss to see how to make use of this method for land reclamation. But by seeing that a friend of mine has used this for one of the landfills in China, but that purpose is actually increase the capacity for the landfill. So by placing this so-called horizontal drainage enhanced blanket to let the rubbish to consolidate to enhance the capacity of the landfill. So that's for a different application. So nevertheless, we have done laboratory model tests as showing over here. Okay, by placing a drainage blanket with a drain in the middle, then we pour slurry on top. In this case, we are using kaolin. So as you know, kaolin is relatively easy to consolidate, so it doesn't take much long for kaolin to be consolidated. In fact, within 3 days, we have reached a relatively high degree of consolidation. That's because it is kaolin which is used. You can see from the water content, our initial water content is somewhere around 96%. Within 3 days, the water content is reduced to somewhere around 55%. The enriched assurance has increased from 0 to somewhere around 25 to 30 kPa. So I mean, at least as demonstrated from this model test, and this method can be effective. And subsequently, Dr. Chen, who was doing a PhD at that time, has carried out many more model tests. Some are using a bigger tank, and some just use a tank which is very tall to study the vertical influences. In other words, to study the consolidation on the different layers of horizontal drainage blanket, not just on the one layer. So some of results are showing over here. So basically, you can see from here. So within a certain duration, you can reduce the water content for the test on top is from 105 to somewhere near 60 to 50%. And the enriched strength has increased from 0 to somewhere around 10 to 12 kPa. So in other words, if you can improve the soil to have an enriched strength somewhere between 10 to 15 kPa with a layer of sand blanket on top, so you can have enough bearing capacity to do normal soil improvement work. But however, I have to say, if you're not, if you haven't waited long enough, okay, if the soil doesn't have achieved a relatively high degree of consolidation, and then the distribution of okay, take back what I have said. Okay, the two pictures showing over here are for two different tests. So one test is for a horizontal drain in the middle, and with the geotech star, as you can see from the graph on top, the geotech star words are written on two sets. So in other words, the first test is using our horizontal drainage blanket. And the second test is by just putting a vertical drain in the middle, but without the geotech star on both sides, okay? So if that's the case, you can see without the using of geotech star layer, the water content distribution is not uniform. You see, you can see in the middle, where you next the drain, and you can have a higher reduction of water content somewhere to 55%. But however, at the points which are further away from the drain, your water content can be still as high as 70%. In terms of undrained shear strength distribution near the drain, which is relatively high, somewhere around 10 kPa, but however, just a few centimeters, that is 30 centimeters away from the drain, and your undrained shear strength is only 1 or 2 kPa. So that actually demonstrates the importance of having this horizontal geotextile layer. And with the layer, so somehow the drainage can be much efficient, can be much effective. So in terms of water content distribution, it can be much uniform, and in terms of undrained shear strength, and the distribution can also be relatively more uniform. But without the geotextile layer, if you just rely on horizontal drains without the geotextile, and you may not achieve the same effect. So we didn't realize this until we have done our model tests. So to conclude, you can use 2 rounds of soil improvement. Use short PVD to form a working platform, and then to do normal soil improvement. But however, if you are doing land reclamation, okay, if your field has not been placed, a better method is for you to use each individual drains. I realized I have not illustrated the construction sequence. Okay, now maybe let me explain and what will be the construction sequence for using this horizontal drain. So the first step is for you to place a layer of the so-called horizontal drainage enhanced drainage blanket at the seabed. By the way, if you have to improve the seabed clay, let's say if your seabed clay is a soft marine clay, so what you have to do is you have to install PVDs from offshore. So this is actually not new. It has been used in Singapore, has been used for many projects in China, and it has been used for the third runway in Hong Kong. So in fact, in the later part of my presentation, there is a video to show all the PVDs are installed offshore from water and from a barge into the seabed. So you can do that to install the PVDs into the seabed first. And nowadays, the PVD can also be cut at the seabed. So in other words, you save you a lot of PVD if your water depth that is 10 or 15 meters deep. Then after that, you can cover your drainage blanket with the slurry or with limepy soil. Once it has been covered, and then you can start to switch on your vacuum pump, or you can start to do your vacuum consolidation. So while this layer of clay is consolidated, and then you can place a second layer of horizontal drainage blanket, and then you can repeat the same process, pump or maybe dump more of the clay to cover the second layer, and then you can start to use vacuum to improve the second layer. And there is a big advantage of using this method, is whatever placed on top. For example, whatever the fuel placed on the first layer of geotextile drainage blanket is acts as a surcharge. So in other words, now your surcharge is 80 kPa and plus whatever fuel placed on top. But of course, for the second layer is the vacuum plus whatever fuel placed on top of the second layer. So your surcharge now is actually much more. So in other words, your consolidation can be much faster. Yeah, then you repeat the same process. Then, of course, for the top few layers, you cannot use your bottom open barge anymore. If you are using lumpy soil, then you have to use maybe clay slurry to finish up for the top layer. But nevertheless, the biggest advantage of using this particular technique is this particular method is, while you're placing the fuel and the bottom layer of the soil is being consolidated, not just under 80 kPa, but under much higher consolidation stress. So by the time you have placed your fuel to the top, basically, your bottom soil has been more or less improved. So I think this will save a lot of time. But nowadays, time is also money, right? You have to borrow money from the bank. You have to pay interest. Okay, so this is a construction sequence. Now let's go back to a summary of this particular method. So vacuum pressure can be applied layer by layer, and while the fill materials are applied, fill materials are placed, sorry, and the fill on top of the horizontal drains and become surcharge, as I have already mentioned. And in this particular method, there's no sand blanket is required, and simply because you don't need to even place your horizontal pipes, and you save time, okay, because the soil is consolidated while the land reclamation is ongoing. But more importantly, it is more reliable for you to predict the settlement. The reason for that is very simple, because once you are consolidating let's say the first layer, okay, you can monitor the settlement. So from the settlement under the first layer, you can back calculate what is the soil property, what is compressibility, what is C sub C. From there you can use the parameter back calculator for you to calculate the compressibility, the settlement for the subsequent layers. So your settlement prediction is much more reliable. And you don't need to have subdivisions. However, it does have its a disadvantage. So that is, you have to install the horizontal drains, the horizontal drainage enhanced sheet offshore, okay, layer by layer. So this can be challenging, as I was told. Okay, with this, so I have finished my first part, which is a construction on ultra-soft soil, okay, particularly with land reclamation using clay slurry as a reference. So now I'm going to change the topic. I'm going to discuss constructions of seawall on soft seabed. So at the very beginning, I mentioned but we also have to have measures to deal with rising sea level. So land reclamation can be one of the methods. Sometimes we may just need to build seawalls, but building seawalls on soft seabed marine clay can also be challenging. Also, in Singapore, we actually do not have much of fill materials. Even with the mud, we don't think we have even sufficient mud for us to do land reclamation. So maybe we have to, to be a little bit more innovative to see whether we can do land reclamation without the use of fill materials. So one of the proposal is by, once you have built your seawall, can we do, construction from the seabed upwards? So rather than, filled with the sand or with the clay, right? If you have a very strong seawall, I think we will be able to do that. So this is one of the proposals. So if we are going to do that, then we have to have a seawall in relatively deep water. Then the question is, how are you going to construct this seawall in soft marine clay, in relatively deep water? By the way, if you have a strong seawall, in addition to the space created behind, you can actually have a floating platform in front, so to extend the space. So these are one of the ideas, how the seawall can be used to build the city from the seabed onwards, as well as with a floating platform on top. Now, my question is how we can build seawall in relatively deep water for the purpose I have just explained. Constructing seawall in deep water is actually not new, because for example, for Pasir Panjang port, for the current past construction, we use big caissons. So if your water depth is 20 meters, our caissons has to be more than 20 meters. In this picture, I think the caisson is more than 20 meters, as you can see from the picture. So you cast this giant seawall in the casting yard, then you tow it to the position where the seawall need to be constructed. By the way, this seawall is, for the port. So in other words, it's the boundary of the fingers, boundary of the land reclamation. But nevertheless, it's built in the same way. So sometimes we have to use a sankey. We have to, dredge out the soft marine clay and replace it by either sand or gravels or stones, and then to form a rubber mount before we can place, 20-meter tall of a big concrete box on top to form a seawall. Well, in this way, you have to do dredging, you have to improve your foundation, and before you can place your seawall. Alternative method is to use the so-called suction caisson. Okay, suction caisson, the concept is not new because it has been used for offshore platform. So the principle is, you can imagine you have a cylinder. If you put this cylinder on top of a seabed marine clay, and if you apply a suction, and the suction will suck this cylinder into the mud. And so you have a cylinder sinking into the mud to form a foundation. Then you can have a seawall constructed on top. So the concept is illustrated by this particular picture. Some of you are familiar with this. So for this reason, so I'm not going to explain in detail the principle of suction caisson. So I'm only going to discuss how we can use a suction caisson, let's say, to form a seawall in relatively deep water. So one of the design is to use the suction caissons to form the foundation. So it forms like cylindrical caisson foundations in soft marine clay, and then with another layer of caissons to form a seawall, as shown in this picture. The construction sequence can be illustrated by this video. This is actually animation. So you cast each individual cylinders, then you can join them together, and then you cast the top cylinders, and then you can assemble them together in the casting yard with a cover plate on top, and then you can tow the whole system, so whole assembled system into where the seawalls need to be installed. And then you apply a suction. And the reason why we are using 4 cylinders is actually to overcome the eccentricity. So if, for example, one cylinder will sink more than the others, you will be able to adjust the vacuum, so to make sure the 4 cylinders will be able to sink evenly into the ground. So that's the reason of having 4 cylinders. But subsequently, someone told me you can try using 3 cylinders. You probably can achieve the same purpose. And then once you have the cylinders, then of course behind you can place fuels to form your land reclamation. But if you just want to form a seawall, so the cylinder will act as your seawall. Of course, there are other technical details as how you join the two different sections together to form a watertight wall. But okay, I don't have time to discuss this. But those details has also been studied in the past. This is the construction, and some of you may be asking, oh, how do you design for such a a seawall, such a foundation? To address this, I mean, again, my PhD student Chen Hao has developed some analytical methods for you to check, just on the back of an envelope, for you to do a quick, calculation on the factor of safeties for such a seawall. Embedded into different depths into the marine clay, with few materials placed behind. But I have to say, if you are going to install your suction caissons into a very soft marine clay, yet you are going to place a few materials behind, itself is not going to have a sufficient bearing capacity or sufficient resistance against the horizontal sliding. So for that reason, you need to improve the soil in front of the suction caisson. Okay, you can use either deep cement mixing columns, or you can use a sand compaction par. In our particular parametric study, we use the sand compaction par because the sand compaction par is probably the weakest among, all the options available, among deep cement mixing, among other methods. So this case study is by assuming we have sand compaction pars in front of the caisson. We want to, using this numerical analysis to identify what will be the length required, for the suction caisson, which has to be installed in front of the seawall. So, over here are all finite element analysis as compared to the analytical method. As you see from the chart, some are from analytical method, some are from numerical method, because this study serves two purposes. One is to verify whether the numerical methods are reasonable, whether they can make sense. The second one is is to use numerical analysis to give us some feeling in what would be the major control factors for the stability of such a seawall. And number three is to identify what are the failure modes. Okay, so basically, the paper is just published in Ocean Engineering. So I don't think I have time to go through the details. So if any of you is interested, I can send you the paper. So what is more interesting in this paper is we even assume for the land reclamation behind the wall is to use a method which is just proposed by us. So use horizontal drainage enhanced drainage blankets or geotextile sheets. So for that reason, we also have information on how these geotextile sheets are designed and given here. Okay, so and this construction process has also been taken into consideration in the design, as you can see from here. So if you have different layers, and how the placement of the layers will affect the settlement, affect this horizontal displacement, as well affect the degree of consolidation calculation, this and that. Okay, and over here the displacement chart or maximum deflection as computed by finite element analysis. All right, so with the suction caisson as the first method, so now I'm going to share a case study. So this case study is for the construction of breakwater for the Shanghai port. And the project was carried out in 2006 or 7, I believe. And our paper was published in 2009 in the Institutional Civil Engineers Journal. Which is published together with Professor Yan Shu Wang from Tianjin University. Okay, so the project is like this. So to create a navigation channel by building two breakwaters on two sides, the whole purpose of having this breakwater is to reduce the need to do maintenance dredging from time to time, because Shanghai port, being I don't know whether it's still the number one or number two, but it's the top 5 busiest ports in the world. So they don't have time to do maintenance dredging because it reduce productivity. So having those two breakwaters, so they will believe you will be able to stop the siltation and to be formed in the navigation channel, and so will reduce the need to do maintenance dredging. And the early section was actually installed in relatively shallow water. And in fact, the land can be exposed when it's low tide. Okay, but however, when they reach the relatively deep water, and that's where particular design or particular construction has to be implemented. The seawall was designed in such a way, so the concrete structure is a semi-circular caisson as shown over here. And it has partitions, so this is a hollow caisson. So once the caisson has been installed, so sand will be filled through the openings on top, so to enhance the gravity. So this caisson has to be positioned on top of a rubber mount, which consists of rocks as well as scour protection layers. Because as I said, this is in relatively shallow water, so scour is still a consideration. Okay, so the deck was constructed along the the black section without much of a problem. But I have to say, those are the very shallow sections. Some are actually exposed when there's low tide, so it has no problem. But once we reach a relatively deep section, shown in the second section over here, and there was a failure. But before I introduce the failure, let me just show you the cross-section of the design. So on top is a semicircular concrete caisson on top, which is sit on layer of rubber mount. The rubber mount was made of a geotextile layer with a sand blanket and with rocks placed on top. On the two sets, we have scour protection layers. And later I'm going to show all the scour protection layers are installed. While during the construction in the second section, and there was a failure after a heavy storm. Shanghai is still affected by typhoon, by some of the heavy storm. So after one heavy storm, some of the concrete segments has settled. I mean, to different depths. Some are settled, for example, 1.5. Okay, here is the indication of the elevation. So the top number is the elevation before the storm. The number below is the elevation after the storm. If you look at the first caisson, so you have the sank for what almost 1+ meters, right? 3.1 minus 1.5. So this is the horizontal settlement, and also one of the sections has slided for few meters horizontally. So in other words, it's not just there's not enough bearing capacity and for the caisson, and also there isn't enough horizontal resistance to the storm. So this is the settlement of one particular caisson, I believe is at this location. So this location, the settlement is the largest. So as showing over here, so with the wave height, with the storm, you see at one stage, the caisson just gave in. The caisson, just sink into the mud. The enhancement of horizontal resistance is resolved by putting pins, as shown over here, at the base of the concrete caisson. So with this, the interface friction has increased. If my memory is correctly, is from somewhere between 0.4 to 0.7. So just by using the pins and using a layer of rubber mat. So what they have done is stick a layer of rubber mat, and in addition to this, and stick some pins at the bottom of the caisson to enhance this lateral resistance and to the storm. This is not to the field, because this is not a land reclamation project. To enhance the bearing capacity, so PVDs was used. So it was believed that once you install and PVDs 10 meters into the ground, and with the rubber mount, so with the surcharge, so probably the seabed will have enough bearing capacity for you to support the concrete segment, the semicircular concrete segment. So how the PVDs are installed from offshore, it is from a barge. So this barge can install PVDs, can install 12 PVDs because 6 on each row. There are 2 rows. So this is the installation process. So 12 barges 12 mandrels were inserted into the ground. And even the anchor plate was recovered for this particular project. But however, for this particular project, the PVD can only be cut at the barge level. So in other words, you have 10 meters of water depth. So you have 10 meters of wastage of your PVD. But for the Hong Kong third runway, the PVD was cut from the seabed. So that will give you some saving for the PVD materials. So for the scour protection layers, there are 2 methods. So one method is to use a sun-filled geotextile tube. So basically you place a layer of geotextile sheet, but on the geotextile sheet, you have like ribs. So these ribs are small geotextile tubes. So you inflate, you actually pump the sand into the tubes while the blanket was placed under the sea. So this is one method. And second method is by placing, these chained concrete blocks, composite on top of the geotextile. So both methods are used. Depends on whether it's close to the caisson or further away from the caisson. So here is the animation to show and how the concrete chain, the block was placed, as well how the thin geotextile tubes was inflated by sand while the geotextile was placed. And so this animation shows how the caissons are installed in place. By the way, the PVD installation is only up to 10 meters. And that's because after the stress distribution, and the conclusion is when the stress is transmitted into the layer deeper than 10 meters, and the intensity has much reduced. So in other words, you don't have to improve the clay below 10 meters. And so here is a comparison of the few wind shear tests before and after the installation of the PVD. In fact, after the formation of the rubber mount. So you can see the increment in the end shear strength, but also you can see, for in the soil where the PVD was not installed, in fact the improvement is little. So that actually indicate if you install PVDs to 10 meters, don't expect the neighboring effect. Don't expect the soil 12 meters deep will benefit from the installation of the PVD. What the monitoring data here is the settlement after the breakwater has been constructed and over 11 months. Okay, I mean nearly 11 months. So within the 11 months, as you can see, there are actually some storms in between, but nevertheless, okay, the settlement doesn't really increase sharply as we have seen in the early failure case. So in fact, all the settlements are within the tolerance. So, and of course, there's no horizontal displacement, and because of the pin and the rubber really helps. So this is a picture after the breakwater has been constructed. Yeah. So with this, it leads to the summary. So we discussed several methods for the formation of a working platform for construction of super soft soil. A method of shell PVD plus a vacuum preloading method has been proposed The two real construction case has demonstrated, and so this is proven. This method is proven to be effective. But however, this method is time consuming, simply because you have to do fuel preloading or fuel surcharge preloading or vacuum surcharge preloading for 2 times. So each time you may have to take 2 to 3 months. So it is time consuming. And also you can only do this by placing all the fuels in place before you can do soil improvement. To overcome this method, another method of using horizontal drainage enhanced geotextile sheet is also proposed for land reclamation using clay slurry. So this is for the first part for soil improvement for super soft soil. Then later on, I also introduce 2 methods for the seawall construction. One is using suction caisson, another one is by using PVDs and to improve the seabed soft marine clay to enhance its bearing capacity for the seawall. So with this, I finish my presentation. Thank you very much. So I'll be happy to answer any questions. And also, I have given a copy of my presentations. So if you like to have a copy, please approach the organizer.
Thank you, Professor Chen, for the great insight of the ground treatment methods and analysis. Yeah, just to highlight that the slides from Professor Chen will be inserted into this webinar, and then all the participants will come to download it. Okay. So we will get down to the questions. So Prof. Chen, I think I have a question from the audience.
How do I see the question?
Let me assign it to you with. Okay.
Oh yeah, I got it. Questions.
Yeah. So the first question is that in terms of the construction methodology, how do we ensure and verify the thickness of each layer of clayey fill material dumped from the floating barge before laying the horizontal drain plus geotextile sheet? The dump clay may distribute unevenly below water. That's a question from one of the audience.
For which method? For the short PVD or for the horizontal drainage blanket?
I believe it should be for the horizontal drainage blanket, because the question also is not so clear.
Okay, for the horizontal drainage, the horizontal drainage blanket is already linked to the horizontal drainage pipe before the installation. So in other words, you don't have to install it below water.
I see. I think that's one more approach that you showed earlier, that when you start to treat or reclaim the land, right? You actually dump the clay fill material into the soil as you are but before this you have already installed PVD. So I think the question is that how do you ensure that every time you dump the clay into the water, that the thickness will remain constant? I think earlier you showed the methodology of reclamation when you are reclaiming the ground layer by layer after you install the PVD. Yeah.
Right. So that refers to this method.
I think there's one more slide when you click on the horizontal drain. Yeah, this one. Yes, this HDEG. Yes, correct. Yeah.
Okay.
So, yeah, this one. Yeah. So the question would be, how do you ensure that dump clay can be evenly?
As you can see, the horizontal blanket is installed from a barge. So in other words, for the other end, which has already been linked to the drainage pipe, linked to the pumps. Okay, so that's not a problem. And the second question is, when you install the second layer, right? How do you ensure the settlement is uniform? Yeah, you don't need to ensure the settlement to be uniform because the horizontal drainage layers doesn't have to be horizontal. Yeah, in fact, even if, because sometimes people may ask me, okay, you cover it with a layer of clay. Although the layer of clay is very soft, but there may be a possibility you may not be sealed 100%, right? So if you have leakage, what do you do? Well, even if there's no vacuum, okay, but because, as I said, you are going to put a few materials on top. So you are still applying fuel surcharge. So the horizontal drain can still act as a drain, but in this case, you cannot apply vacuum. Okay, but by seeing that, you see, if you once you put the first layer of slurry, and the vacuum may not be 100% sealed, but when you put the second layer, the third layer, and you actually enhance the water tightness, correct? So maybe in this process, so the water tightness can be improved. So in other words, so the vacuum can still be in effect. Or even if there's a certain leakage, you still can apply vacuum. It's just your vacuum efficiency is not there. It's just like when you switch on your air conditioner, but yet you open your window, your room can still be cold. It's just not be cold as when the windows are completely closed. Yeah. So from that point of view, even if your base layer may not be even, to me, it's not a big problem because it is soft. Yeah.
Okay, thanks, Professor. Let's move on to the second question. How do you maintain the surcharge height and slope gradient under the sea? Is there any checking or maintenance to be carried out?
The slope gradient of this.
Yeah, slope gradient, I think, of the field, under the sea. I think when you're feeling, I think it will be natural slope, right? Natural slope when you
this particular method. Yeah. But because you're going to put a thin layer, so in my opinion, you shouldn't be more than 3 meters. So if you only put 1 to 2 meters, it is a small slope. Yet you're spread to cover a larger area. So you only talk about the boundary. So I don't think the boundary will matter that much. Particularly when this is relatively deep water, so you don't have a scour.
Okay. I see. All right. So I think we have another question.
Oh, but by the way, if it's a slurry, the slurry will automatically level it off as those who use slurry. Slurry will form a very, very gentle slope of even few degrees.
One of the audience asked, how do you monitor the settlement? I believe probably, especially when you are talking about this approach, right? When you are expecting consolidation which will occur under the seabed while you are filling up with the clay. So how do you ensure that the consolidation has achieved the required strength and also the degree of consolidation? Is there some form of instrumentation that can be installed?
Yeah, you are right. For our laboratory monitoring, we of course we can put some settlement markers at different depths to monitor the different settlement. If you put them layer by layers, you can put some markers, let's say on top of the horizontal drainage blanket before you place the other layers. Also, you can calculate your degree of consolidation using the pore pressure installed, pore pressure measured. So again, you can put pore pressure transducers into the clay layer and to measure the pore pressure.
Okay.
So in fact, if you go to this paper, and there
do
are
we install
methods,
like a settlement gauge or rod settlement gauge all the way down?
I have not really, think through how you do instrumentation for this particular method. But I thought that you can just put the settlement markers when you place your horizontal drains layer by layer.
Okay, no problem. So probably let's go to the next question. Let me share.
Okay, in the paper, let me see whether I can go to the next slide. Yeah, but by the way, this method has been published. In the published paper, we actually have discussed a method to calculate degree of consolidation based on settlement and based on forward pressure.
Okay, I think for those participants who are interested to understand more, probably you can email Prof. Chu, and Prof. Chu can share the paper probably, or yeah, that way will be much better. Okay,
Maybe
I think
what I can do is I will send the organizer the papers.
Yeah, can.
For those of you who is interested in the presentation, you can get the paper and the presentation together.
Yeah, I mean we have shared the presentation slide, so if those who want to know more this, probably can email to us IEM, yeah, and then we will try to share the technical paper. Yeah, no problem. So for the next question is that will the geotextile membrane or geogrid interfere with the subsequent deep foundation work?
This refers to the early method, right?
I think so, yes. Early vacuum method, after you've completed everything, and then you will be building buildings from the top, right? Yeah. So I think one of the audience wanted to know if there is any problem with, or I would say resistant, yeah, due to the membrane and geogrid.
Reason, yeah, I don't think so. The reason for that is because this is a real project. Okay, so PVDs has been installed subsequently. So there's no problem for you to install PVD. Yeah.
Yeah, okay. So let's go to the next question. When installing PVD offshore, how is the accuracy based on your available case study? Can the specified spacing be achieved?
I believe so, although I do not have data because it didn't occur to me this can be a problem. But however, if you look into the batch, look into the frame, I have visited the two of such machines, one in China, another one in Hong Kong for the Hong Kong third runway construction. Okay, the frame is huge. I don't think the frame is going to bend like the mandrel, in our normal PVD installation. Our normal PVD installation, it has an inclination of a few degrees. So for this batch, I don't think the inclination will be as bad as the normal PVD, simply because it is much rigid. But by seeing that, it actually doesn't matter. So even if your PVD is installed not vertically, it doesn't affect your discharge function.
Okay, so I hope this answers the question.
There's a theory for it. I don't have time to explain this. Okay.
Yeah,
due to spatial average. So if your PVD is very long, let's say more than 10 meters, so it actually average off. So even if, for example, a few PVDs are very close together, yet a few PVDs are relatively further apart. It is overall effectiveness which matters. So this is based on a statistical principle called the spatial average.
Okay, so let's move on to the next question. Can the suction caisson being implemented if the perimeter of the reclaimed land exhibit irregular seabed profile?
For which method?
Suction caisson. I think
suction
when
caisson,
you talk about suction caisson.
That's a very good question. Yeah, the suction caisson is not meant to install to your hard structure. So this is more like a floating caisson. So it relies 100% on the frictions.
I see. So if there's any irregular seabed profile, can the suction caisson being installed there?
As long as you can penetrate. Yeah, in fact, the suction caisson is more challenging for shallow water, simply because you don't have enough suction. The sources of your suction is water depth plus 1 atmospheric pressure. So imagine if you have 30 meters of water, so you have 380 kPa. The 380 kPa may not be able to, suck your big caissons a few meters into the mud. That's the challenge. But on the offshore, it's not a problem because you have water depths of a few hundred meters. Let's say if you have 300 meters, you have available suction of 3,000 kPa.
Yeah. Okay.
So this is a challenge. But seeing that, we have done a project. In fact, we hold a patent for install suction caissons in shallow water. So for those of you who are interested, I can share with you how to do the installation in shallow water if you encounter difficulties for the penetration of caissons.
I think the suction caisson approach is so far it's not a very common approach being used, right? Suction caisson. I think like what professor has presented, probably 1 or 2 places has used this approach, isn't it?
You are right. Yeah, it is probably more used for bridge piers rather than for seal. Yeah, but by seeing that there is an experiment or other tests done in Tianjin.
I see. Okay.
A very long stretch, maybe even up to a few hundred meters of seawall installed in this way using suction caisson. You can actually see it from a Google map.
I see. I have a question for myself. Just wondering, especially for the vacuum approach, where you have an approach where you are having vacuum without the sand blanket. So, from your point of view and your research that you have carried out, right, is it effective in terms of, because there's no sand blanket there, and then is it that the efficiency be affected?
Why, if the connection is good, if you use PVD with a high discharge capacity, I think the discharge capacity of the PVD is an important design parameter. Yeah, then the efficiency shouldn't be very much different from the normal design using a layer of sand blanket. In the old ways, in China, the PVD was wrapped around the horizontal drainage pipe. That method doesn't work. The efficiency is very low. So because of that, it has been replaced using metal coupling. If you look into this slide, yeah, using this slide, okay, originally you see the black coupling, the black connector, originally was used in plastic, but somehow the plastic tend to crack. So later on they changed this into metal. So with the metal, I think the efficiency is much improved.
I see. So the connection is very important.
Yeah, the connection is very important.
And it's kind of like labor intensive because you have a lot of point, and at each point you have to make sure it has been connected properly. Yeah, so it will be I think for a large area, it will be a challenge, isn't it?
You are right. You are right. Yeah, but I mean, I have seen the one in Jakarta. In fact, it's actually very fast because in Jakarta you use a different coupling.
Ah, I see. Is it a metal coupling as well?
No, it's not a metal coupling. I cannot share because I'm not given the permission to share.
I see. No problem. Maybe we can talk later. Anyway, so we have a next question. How do you construct shore protection such as rock revetment over reclamation slope using soft clay? Would the rock not sink into the soft clay? Maybe I will share you this question as well.
The last case study, right, for the Shanghai port.
Yeah, the shore protection such as rock revetment over reclaimed slope using soft clay. I think, yeah.
Using soft clay, I don't have such a case. I only presented two cases. One is suction caisson, another one is the concrete segments.
Yeah.
Concrete.
So probably it's
general
question. Yeah, general question. So it's more on like shore protection, if there's any shore protection. But if you are doing a seawall, there's no need of shore protection, isn't it? But if you are doing a normal reclamation,
yeah, in relatively deep water, you probably don't need scour protection. In fact, for the changing case, we didn't do all set of the concrete cylinder, the suction. They didn't do any other protection.
Yeah.
So the settlement I was told is very minimum so far, because that has been installed for quite a number of years. The first few years they were still monitoring the settlement. The settlement was very little, and there's no scour as I was told. Although the certain section is on relatively shallow water. So I don't think that's a problem. But if you talk about the rock, rock bound on top of soft clay, you have no choice, but you have to do Sankey. You have to dig out the soft clay, replace it by good soil, by rock, by sand. All you have to do deep cement as
to improve it, as an improvement of the
yeah.
Okay.
The other method, of course, you can use so-called columns, embankment columns. So you install maybe deep cement mixing columns. Then use a load transfer platform before you put the
to create a formal platform before you put the rock.
The rock or sand band.
Okay, I think do we have another question? How is the resulted settlement of the horizontal as compared to the vertical drain? Result probably is not so clear. How is the resulted settlement? Horizontal.
Using horizontal drain resulted settlement. Yeah, in fact, your settlement is independent of your drainage. It doesn't matter you use a horizontal drain, use a vertical drain. If we ignore the small reinforcement of the plastic itself, it doesn't contribute towards settlement. So you only improve the rate of consolidation. So the will still be the same. Just like for you put fuel surcharge on top of a layer of compressible clay, whether it's a PVD or not, in theory you have the same amount of settlement. You just using PVD, you can settle much faster. That's all. But of course, during the installation of the PVD, you actually disturb the soil. So that process itself causes some additional settlement.
Yeah, true.
Otherwise, in theory, if you don't consider the construction process, so the settlement should be the same. The same goes for horizontal trees.
Okay, the next question we have is that bamboo mattress will form part of the embankment of land reclamation permanently. Will the bamboo get rotten over time and cause side effect to the embankment, such as differential settlement in the future? I think there's one slide that you show using bamboo, right?
No, the bamboo more for the formation. Okay, when I mentioned about bamboo, I use that as an example to illustrate a method for the formation of a working platform. For the formation of working platform, it actually is a temporary platform. But by seeing that in Indonesia, but they have used bamboo a lot. I mean, the same goes in Malaysia, I believe. I mean, particularly East Malaysia. So my belief is if the bamboo is below water table, it is actually durable.
Yeah. So even if they are, I mean that because they will be inside the soil, even if they are, they will take for bamboo, the nature of the bamboo because of the fiber, it will take a very long time for them to rot, and to even do that if they are submerged underwater, they will be very durable over a long distance of time, right? Isn't it?
Yeah, I believe so. Yeah, because you know, in China there is a wooden pagoda which has been there for, you know, okay, maybe up to 1,000 years. I remember during one of the presentations, the speaker said, "Oh, the reason why, you know, the pagoda is supported by, you know, timber piles. The pagoda can still stand there for so many years is because the timber piles are below water table, something like that."
Yeah. So, okay, I think we have answered quite a number of questions. I think we have about less than 8 minutes before we end our webinar. If there's any more question, please post it right now. If there's no more question, I think we can wrap it earlier. But let's just wait 1 or 2 more minutes. Yeah. So I would, yeah, IEM appreciate your time, Prof. Chu, for coming and presenting us with this excellent presentation. Yeah. So I think yeah. So we appreciate your time. I think so the good thing about webinar is that if you can still present even if you are anywhere around the world. So it's kind of like beneficial to a lot of our engineers as well.
Thank you, Alan. Yeah, it's my great pleasure to have this opportunity to interact with colleagues from Malaysia. So if you have other questions, I mean, please feel free to send me an email. I will be more than happy to continue the discussion with you.
Okay, so I think so far I have not received any more new questions. So if that's the case, I think we will end this webinar right now, about 5 minutes before 5. Yeah, thanks a lot, Prof. Chu Chen, for your time and your effort in presenting for today's webinar. I believe your talk has benefit us, yeah, most of our audience. Yeah. So thanks again. And then, of course, we are looking forward for your next webinar or even physical talk. If there's a chance that you come to Malaysia, yeah, we will extend our announcement. Yeah.
Well, thank you very much, Alan. And also, thank you for the very good questions. Yeah.
Okay, I think we can end it. Okay, thank you, everyone. Have a good day. Thanks.
Thank you. Yeah, bye-bye.
Bye-bye.